Now we will do a few problems using the basic definition of first variation. And we will do these problems carefully because these kinds of manipulations are very common in nonlinear finite elements, and we will have to do them all the time. Let us start with a scalar function of a second order tensor A. So a scalar function, let's say phi, of of a function A, and let phi be defined as determinant of A, which is a scalar. So phi A is determinant of A, and now we want to find the directional derivative of this quantity, determinant of A, in the direction of another second order tensor T. So see how we have generalized things. Now we have a scalar function of a second order tensor in the direction of another second order tensor. So what this physically represents is difficult to visualize, but mathematically this is a completely doable operation. So what we want to find is a directional derivative with respect to A of the function determinant of A in the direction of the second order tensor T. So this is the quantity that we want to find. Later we will sometimes drop these subscripts when things are self-explanatory, but for the time being we will carefully be putting the subscripts so as to remind us of what we are taking the directional derivative, what we are taking the derivative against, and which direction we are taking the directional derivative in. So using the basic definition, so this is what we need to find. Using the basic definition, what we have to do, we have to now do determinant of A plus a small perturbation given in the direction T, so epsilon of T. So this is what we will have to evaluate, and we will have to do that for d epsilon. We have to do d epsilon of this for epsilon equal to 0, and this will give us the quantity that we want, which is this. Now the first step is kind of easy. So we take this quantity and we write it like this. So we can write determinant of, we can take A common, and we will have I plus epsilon A inverse T inside, and then we can use the fact that determinant of A times B is determinant of A times determinant of B. So this will become determinant of A times determinant of I plus epsilon A inverse T. And then the d epsilon, of course, does not apply to that A because it does not contain epsilon. So the d epsilon applies only to this part. So we have determinant of A, taken out determinant of A, then the d epsilon equal to 0. We have to take the d epsilon of this, put epsilon equal to 0, and we have our answer. Now, how do we get this determinant? Here comes a trick. When we solve eigenvalue problems with tensors, we know that we get to a characteristic equation, and we set that characteristic equation to equal to 0 in order to solve for the eigenvalues. I hope you remember that. Now we are going to use that result. There's no there's no eigenvalue problem here, but we will use this result because we know that the characteristic equation of any tensor, second order tensor B, is determinant of B minus lambda I, where lambdas are scalars, will turn out to be eigenvectors if you set this equal to 0. But we are not interested in setting this to be equal to 0. We just need the form of this quantity. So we know that determinant of B minus lambda I is this, where I1, I2, I3 are the invariants of B. So these are the first, second, and third invariants of B. And from your eigenvalue, from whatever you know about eigenvalues and eigenvectors, you know that I1 is trace of B, I2 is trace of b square minus trace b square, and I3 is determinant of b. So if you set this equal to 0, solving this cubic equation will give you the three eigenvalues, but we are not doing that. We are not interested in doing that. We just are interested in this identity that determinant of b minus lambda I is equal to this quantity. And now we will just set lambda equal to -1 and b equal to epsilon a inverse t, which is what we had in the previous case. So this is what we will set it to, and then use this equation. So when we set lambda equal to -1, this becomes determinant of lambda is -1, so this becomes I plus epsilon a inverse t, which is what we want to evaluate, and that will be equal to lambda equal to -1, so this is equal to 1. This is equal to 1. Then this is equal to trace of epsilon a inverse t plus plus, because lambda is again -1, the second derivative of a second invariant of epsilon a inverse t, let's call that 2, plus the third invariant of epsilon a inverse t, let's call that 3. Now all of these will contain terms 2 and 3. Remember, 2 is something like trace of epsilon a inverse t whole square minus trace of epsilon a inverse t square, and maybe there's a half here. So it's something like this, and each of these will contain epsilon square. Each of these terms will contain epsilon square. Similarly, this 3 is determinant of epsilon a inverse t, so that's equal to 3, and this will contain epsilon cube actually. So when you take derivatives d epsilon, these will contain, either this will contain epsilon square and these will contain epsilon, so that when you set epsilon equal to 0, these terms all will go away. So we do not need to worry about these terms. This, when you take derivative with respect to epsilon, this will actually contain no epsilon, and therefore this is a term that we should be considering here. So I will write this determinant of epsilon a inverse t plus I equal to 1 plus trace of epsilon a inverse t, which is here, plus higher order terms in epsilon, which we don't need to worry about. Now I have to do d epsilon of this. I have to do d epsilon of this, and d epsilon of 1 is of course d epsilon of 1 is of course 0, and so I'm doing d epsilon of this. So d epsilon of 1 is 0, and d epsilon of this would be epsilon times trace a inverse t, and then d epsilon of that would be just trace a inverse t, and that is what remains. And we had this data earlier. So this is the result. This is the directional derivative of the determinant of a with respect to a in the direction of t. That's what this result says. So when we did high school derivatives, so if we have a function of f g of x, so f is a function of g, which is a function of x, and we want to take d dx of f. So what we do is use the chain rule. So we do df dg and then dg dx. So this is how we do chain rule of derivatives. Now let us derive a similar result for directional derivatives. So chain rule for directional derivatives. So f of x is an implicit function of x where it is equal to some f star of b of x. So implicitly it's a function of x, but directly it's a function of b, which is in turn a function of x. So what will be the directional derivative? What will be the directional derivative of x of f in an arbitrary direction u? So f can be a vector, tensor, or scalar function, and so can be u. Now, uh, so we have already seen this expression. So this is the Taylor series expansion of x plus u, which is fx plus the directional derivative of x in the direction of u. So this is what the direction Taylor series gives you. Now, fx plus u is is equal to f star b of x plus u. So when we have b of x plus u, we can write this b of x plus u using again this Taylor series as b of x plus directional derivative of b with respect to x in the direction of u. So we can write this thing inside the brackets as this, which is what we have done here. So now we have f hat of bx plus f hat of bx plus this quantity, which can be written as again using this, and instead of x now we have bx. Instead of this quantity we have instead of the direction u, now we have delta x bu, that takes the role of u. So this would be f hat of bx, so that's like this, plus directional derivative with respect to b of f hat in the direction of, right. So that's what this step does. Now f hat bx is of course fx, and then this is the second term that we have. So to calculate the directional derivative of, to calculate delta x f of u, which is fx. So to calculate fx of u, x plus u, f of x plus u, you will have fx plus delta x f in the direction of u. That's what you have, fx plus u equal to fx, and then this must be delta x of f in the direction of u. So delta x of f, if you have to calculate delta x of f in the direction of u, you have to take, where f is a function f hat of bx, then you first have to take directional derivative of b with respect to u, and then take directional derivative of that with respect to b, which is exactly analogous to what we did for the ordinary derivative here. So this is the chain rule for directional derivatives. Now consider the scalar product of two functions. So let's say one function is the second Piquet stress, and then you have the Green-Lagrange tensor, and we want to find the first variation of phi, the scalar phi, due to a variation in E. So what we want to find is del phi as a function of E, and so there's no variation in S, there's a variation in E only. So when you need to do this, what you have to remember is what the basic definition of del phi E is the directional derivative of phi in the direction of delta E with respect to E. Okay, so this is the definition, and this definition the formula for this definition is you to take dd epsilon of epsilon tending to 0 of phi evaluated at E plus epsilon delta E. Now phi is given by this function. So at so this quantity would be S times E plus epsilon delta E, which will be equal to S times E, which is not a function of epsilon, plus epsilon S times delta E. So when you take dd epsilon of this goes to 0, this epsilon goes to 1, and you are left with S delta E, which is the answer here.